Great. Well, hi, my name's MacKie. I'm an assistant professor at the University of Florida, and I'm going to share some of my thoughts on how and how not to use machine learning to bring together these different pieces of information to map subglacial topography. The way I see it, we have two types of information to deal with. We have spatial relationships within a variable and multivariate relationships between all of these different sources of information we've been discussing. So there's an interpolation problem and an estimation problem. And I'm going to talk about some of the tensions between these two things and how we can elegantly bring these types of information together. Before I get into the methods, I'm going to talk about our objectives when we're doing data assimilation, and I'll close out by talking a little bit about data management. Okay, so I think it's important to talk about what we want in a bed map before we start making it. So obviously we want accuracy. We want accurate bed elevation values. But we might also want morphological realism or realistic topography. However, it's important to keep in mind that these two things are opposite objectives. If we have some measurements, we can come up with a deterministic or most accurate solution, or a stochastic or statistically realistic solution. In my work, or in spatial interpolation, this can be done deterministically with kriging or with geostatistical simulation. So in kriging, we use the spatial statistics of the observations to find the most accurate bed elevation value at a given location. And in geostatistics, or in geostatistical simulation, the objective is to reproduce the spatial statistics of observations. So this example was some ice-free land in Greenland where I extracted lines to represent radar surveys, and I did a deterministic and stochastic interpolation. And it's important that we choose which one of these we want to do at the outset, especially because it can be very easy to do some machine learning problem where we set a loss function where we're trying to optimize both of these things, and we end up finding something in the middle which would not be very helpful. So we want to be pretty clear from the outset which of these we want. And I think geostatistical simulation is particularly useful for when we want to, for example, quantify uncertainty in ice sheet models with respect to topographic uncertainty. We can use geostatistical simulation to generate ensemble realizations of the bed and then do ensemble ice sheet model runs. So if we want to quantify uncertainty in ice sheet projections with respect to topographic uncertainty, this is how it should be done. Okay, we might also want robust uncertainty quantification methods. There are some interpolation or estimation methods that are better at quantifying uncertainty than others. So one question we might want to ask ourselves is it more important to have slightly better accuracy or more robust uncertainty quantification methods? The other thing we should care about is internal consistency within the bed map. So right now we have a lot of different methods and different variables used to estimate topography in different parts of Antarctica. And that's unavoidable to some extent, but the problem is that a bed elevation value in one location might encode different information or mean something different than a bed elevation value in another location. So that just that creates problems down the line potentially, especially if someone were to use this topographic map as an input variable in like a neural network, where those differences in information in each of those bed values could cause problems. We might also care about reproducibility or open sourceness. According to FAIR principles, the protocols used should be open source and free, so that might dictate how we want to make a map. And then the final things we care about are the utility of the bed map, the objectivity, or trying to minimize ad hoc or human decisions when making a map, and the interpretability of the final product. And that brings me to this last point where the more information or levels of complexity that go into a bed map, the more limited the range of applications. So I like to imagine this curve where as the complexity of your algorithm increases, there comes a point where you have diminishing returns in terms of accuracy, and your utility goes down. So for example, if we make the assumption that topography is always oriented along ice flow direction, we can probably squeeze some more accuracy out of our maps, but we're also limiting the end or the range of applications of the final product. So I think it's important to discuss where this dipping point is for us. Okay, with those objectives in mind, let's talk about some data assimilation techniques. Before I talk about how to combine interpolation and estimation, I'm going to focus on the estimation component first. We heard a lot about mass conservation, gravity and magnetic anomalies, the potential of using ice surface expressions to constrain the bed. And this is very challenging because a lot of these things are non-linearly related to the bed. So inversions are one of the main ways we can incorporate this information into bed elevation estimates. However, some of the challenges is that these inversions are highly underdetermined, and so we can only solve them through making a lot of simplifications and assumptions, maybe some regularization, which increases the smoothing. Maybe we have to do the inversions along lines and then put things together. And then we also have to deal with the boundaries of regions where we used an inversion to estimate the bed versus some other method, and we have to line them up somehow. Some of the ways we can deal with this is through Bayesian approaches, like this study by Doug Brinkerhoff, where he was using Bayesian statistics to sample the inversion parameter space. Thomas Teisberg, who's here, also used physics-informed neural networks to do a mass conservation inversion. And in this project, he was predicting both the depth average velocity and the bed elevation, so he was minimizing some of the assumptions about the relationship between ice surface velocity and depth average velocity, and also able to seamlessly map slow-flowing and fast-flowing areas. But there are also a lot of drawbacks to using neural networks. There's the famous lack of interpretability or black box problem. They're notorious for not extrapolating well. Convolutional neural networks, which are the main mechanism for looking at spatial relationships, can only work with continuous gridded data, which we don't have with radar. And they're pretty bad at reproducing geostatistical properties. Also, we can expect that a bed map product is going to be used as an input into neural networks. And I think we want to be cautious about building neural networks on top of neural networks. Okay, so let's talk about the spatial component. This is a figure by MacKie showing a comparison of kriging, mass conservation, and streamlined diffusion for interpolating topography. Kriging has a very formal mechanism for quantifying uncertainty and is very robust, but it does leave these very prominent bullseye artifacts. Those can be mitigated through streamlined diffusion. However, streamlined diffusion requires a lot of assumptions about relations between the bed and ice surface or ice flow direction, and there isn't as rigorous of an uncertainty quantification method. Thankfully, I think there are ways that we can maintain some of that continuity while still using kriging. Kriging with anisotropy can be used to maintain some of the continuity in geologic phenomena. However, it usually assumes that the direction of anisotropy is constant, which doesn't really apply here. We can do kriging with locally varying anisotropy by using non-Euclidean distances to quantify our spatial relationships. So that can be one way to deal with these more complex channel features. Or we could do something like John Goff did at Thwaites, where he did a coordinate transformation to straighten channels and then interpolated those transformed channels and then back transform them. But I actually don't think it needs to be that complicated, because a lot of this anisotropy in the topography is in the long wavelength behavior, not the short wavelength behavior. So we can decompose the long wavelength and short scale topography and do some kind of long wavelength estimate of the channels or more like nonlinear features, and then Krieg the residual. So the way I think this can be done easiest is with radial basis functions, which you can think of as being like a non-parametric smoothed version of Krieging. So you need to set some kind of smoothing factor, which I've shown here in the middle and on the right. And I think it's best practice to set the smoothing factor to be comparable to the biggest gap in measurements that you have, so that we have this internal consistency. So that means that the quality of this radial basis function trend is going to be dictated by, I guess, the worst part of your map. But I think the simplest solution is to use RBF to do the trend, Krieg the residual, add them together, and that way you get something that quantifies your uncertainty and has more of this continuity. Using geostatistical simulation, we can also capture more complex features, for example, by training on topography on the Laurentide ice sheet to fill in the gaps. Okay, so how do we combine these things? Option one is through co-Krieging, which is a multivariate form of Krieging, but we have to assume linear relationships between primary data like radar and secondary information. So if that secondary information is gravity anomalies, and we can find some linear relationship between radar and gravity anomalies, this would be a really good way of combining the two. Similarly, we can use some kind of hybrid approaches. For example, this is a synthetic case study using a physics-informed neural network with a radial basis function activation layer, and use that to make some initial estimate, and then use co-Krieging to refine that and merge that with the primary data. My favorite option is through geostatistical inversion, and the idea is that you generate geostatistical simulations of a geological phenomena, forward model some kind of synthetic geophysical observations or maybe ice flow, and then reject the ones that don't match real observations. Or in this case, they were iteratively resimulating components of a simulation grid until it converged with observations. So I think this would be a really good way of accounting for all of these pieces of information. Finally, let's talk a little bit about data management. This is some radar bed elevation measurements gridded at different resolutions, and we can see that the minimum bed values are very different, so we need to be careful when we're doing this to interpret things based on the resolution. When you do the interpolation, the uncertainties for different resolutions are going to be different. So I think it's worth doing something like RIMA and providing estimates at different resolutions so that we're not biased by whatever this was gridded at. And then finally, data formats. We mostly work with GeoTIFFs, which are compatible with GIS software, but in a lot of other programs, it's much more convenient to work with something like a CSV format. However, these two file types are very memory inefficient, and given the volume of data that our field creates, I think it's worth considering some of these like big data file types like JSON, XML, and Parquet. And these file types can reduce your amount of data or the space of your file by an order of magnitude, and you can load it much more quickly. So I work with Parquet files. I think they're very well supported and easy to use. So I think this is a good opportunity to establish what our big data standards are. And maybe we want to provide bed maps in GeoTIFF and some other format so that, that it's useful for different people. So in summary, our choice of bed mapping method depends on our objectives. Often the simplest solution is the most useful one, or least likely to be wrong. Stochastic simulation is a good way of sampling your parameter space, and reducing the the big measurement gaps can help strengthen some of these methods all throughout Antarctica. And finally, I think it's time to come up with big data norms. Thank you.